In this supplementary section, we're going to be learning some tips and techniques for computing modular inverses. It of course requires you to know what modular inverses are, but also the successive squaring algorithm will be helpful in certain places. So let's just start right off with an example. Find an integer x equivalent to 3 inverse modulo 11. Now, since 3 and 11 are relatively prime, there is an inverse to 3, so this isn't a pointless problem. So what we're trying to do is solve 3x is equivalent to 1 modulo 11. In other words, 3x is a multiple of 11 plus 1. It doesn't take a whole lot of effort to notice that 3 times 4 is a multiple of 11 plus 1. It's just 11 plus 1. Therefore, 4 is equivalent to 3 inverse modulo 11. In that case, however, just by sort of staring at, I want 3x to be 1 larger than a multiple of 11, it didn't take a lot of effort because the first multiple of 11 gave us 11 plus 1, which is 12, and we can then sort of say, I can just do 3 times 4. The solution isn't always going to be so immediate. For example, find an integer x equivalent to 6 inverse modulo 13. So again, since 6 and 13 are relatively prime, there is a solution, and we want 6x to be a multiple of 13 plus 1. So what we can do is we can list out multiples of 13 and add 1 and see if those are multiples of 6. On the right-hand side there we have 1 larger than a multiple of 13, and then we'll just check, can I make that 6 times something? So 13 plus 1 is 14, which is not divisible by 6. 26 plus 1 is 27, which is not divisible by 6. 39 plus 1 is 40, which is not divisible by 6. 52 plus 1 is 53, which is not divisible by 6, and 65 plus 1 is 66, which, is divisible by 6. So we can say that 6 times 11 is 1 larger than a multiple of 13. So therefore, 11 is equivalent to 6 inverse modulo 13. So in general, how can we find something equivalent to A inverse modulo n? Using the approach from the previous slide, we simply list out multiples of n and add 1. As we go, we check to see if we have a multiple of a, the thing that we are trying to find the inverse of. As soon as you do, what you have is a solution to this equation right here. A multiple of a is a multiple of n plus 1. Therefore, this x will be the inverse of a modulo n. This approach is fine for small numbers, but it can become pretty unfeasible. So for example, if I want to find something equivalent to 38 inverse modulo 443, what we'd be doing is we'd be computing multiples of 443 and adding 1, and then checking if they're divisible by 38. It's not impossible, it's just pretty impractical, especially since the solution will actually be the 35th multiple that we find. So it's going to take a while. This method for finding A inverse modulo n will take, on average, around n over 2 steps, because you're just listing out multiples of A, and on average you're going to have to go through about half of them before you find it. Is there perhaps a faster method? Well, recall, A inverse modulo n exists if and only if A and n are relatively prime. But under this scenario, A to the phi of n is equivalent to 1 modulo n. Since phi of n is going to be at least as large as 2, we're going to rewrite this as a times a to the phi of n minus 1 is equivalent to 1, instead of just a to the phi of n is equivalent to 1. But observe what we have now is a times something is equivalent to 1 modulo n. In other words, we have found the inverse. A inverse is equivalent to a to the phi of n minus 1 modulo n. So to compute A inverse, instead we can just compute a to the phi of n minus 1. Now, if we tried to do this directly, we'd be multiplying a by itself over and over again, and we'd have to do one multiplication for each value in the exponent, so it would take about phi of n minus 1 steps of consecutive multiplication plus division algorithm to reduce modulo n. Now, that's a lot of work, but it is generally faster than the n over 2 steps that the earlier approach would have taken. But the successive squaring algorithm provides a much faster way to compute exponentials. It only takes about the logarithm of the exponent steps to complete. So with the successive squaring algorithm, we can compute modular inverses in roughly log 2 of phi of n steps. And the binary logarithm of phi of n is a much, much smaller value than phi of n is once n becomes large. That means if we're able to program our own tools, the successive squaring algorithm combined with Euler's formula gives us a very convenient way to compute modular inverses. For example, let's assume that we can quickly execute the Euclidean algorithm and we can also quickly execute successive squaring. Determine whether 154,867 has an inverse modulo 704,867 or not. We are actually given here that 704,867 is prime. Well, inverses exist if and only if the two numbers are relatively prime. We don't even need to run the Euclidean algorithm to determine whether these two are relatively prime. In general, we might have to. We were given that the base is prime. The other is smaller than that, so it's definitely relatively prime to it. Therefore, 154,867 inverse is equivalent to that number raised to the phi of 704,867 minus 1. Since the base is prime, it's easy to compute the value of this Euler-Totient function. Phi of 704,867 will be 704,866 because we were given that it was prime. If we weren't given that the base was prime, we would have to factor it. And then we could apply our formula for computing the Euler-Totient function on prime factorizations. But in this case, since we were given that the base is prime, we know the value of the totient function, and it's easy to subtract 1 from that. So 154,867 inverse is equivalent to 154,867 raised to the 704,865. Modulo, of course, 704,867. Using the successive squaring algorithm, which we've assumed we can execute quickly, 154,867 raised to the 704,865th power is equivalent to 366,791 modulo 704,867. So we have found the inverse. Okay? A number to the phi of the base minus 1 is a way to compute the inverse, and this is a convenient way to do it, assuming you have technological aids to run the successive squaring algorithm pretty quickly. However, a few problems can arise. What if you don't have a convenient way to execute the successive squaring algorithm because you have to do problems by hand because your unreasonably cruel math professor has forced you to do so? Well, handheld calculators will generally start to fail you. If you start trying to compute 154,867 to an enormous power, a lot of people are going to start by simply punching that into their calculator. Most calculators will simply give an error. The number is just too big. Even those that do report an answer will report it in scientific notation, something like 2.3433 times 10 to the 3,658,220th power. Okay, that's a good approximation when you need to do scientific work. But if you're reducing modulo n, every single digit counts. An approximate value of the number is still going to be off by a very, very large amount. This form, we only have the first 10 digits or so, but there are a great deal many digits. In fact, since it's being multiplied by 3,658,220 powers of 10, that's about how many digits it's going to have. So assuming you could even fit 2,000 characters on a single page, which is a rough estimate, it will still take roughly 1,800 pages just to write out this number. Okay, so a calculator is not going to show you the whole number, but if you want to reduce it modulo n, you really need to know every single digit. So we definitely need technology to simplify this, and many students, what they do is they'll do a quick internet search for like compute values modulo n or something, and you'll find a wide variety of resources, a lot of which are sort of personal web pages coded by school instructors, and you'll find a whole bunch of different things this way. But I've found a lot of these, personal web page type things are programmed pretty poorly, and when the numbers get too big, they are simply wrong. So if you find some random web page that says, I can compute values of one thing modulo another, it's probably not coded to be able to handle extremely large values, and it may give you wrong answers. Wolfram Alpha, okay, here's a shameless plug, they're not a sponsor or anything, but wolframalpha.com is a powerful computational tool. I recommend it. It will give you correct responses. If you just type in 154,867 to the 704,865 mod or modulo 704,867, the time it takes to perform the computation is less time than loading the web page, and it will just show you the result. So some practical advice for computing modular inverses. you're generally not allowed to use the internet on exams, so Wolfram Alpha is great for completing assignments, or if you need to do this for other reasons, but if you're doing an exam in a class, you're probably not going to be allowed to use it. You might be. Some courses might be built around the assumption that this computational stuff is like done for you by the internet. But if you're only allowed to use a handheld calculator or even no calculator at all, as long as you practice, executing the successive squaring algorithm is quite possible to do by hand, assuming you're not trying to do stuff with unreasonably large numbers, also assuming that you can multiply, add, and subtract integers of moderate size. So for example, computing 7 to the 22nd modulo 90 I would not consider to be an unreasonable question. All you have to do is execute the successive squaring algorithm. The exponent can be converted into binary quite quickly by hand. Now you have to square and then reduce modulo 90. 7 is 7. You square it, you get 49, which doesn't reduce mod 90. 49 squared isn't necessarily fun, but many people will recognize from algebra that x minus 1 squared is x squared minus 2x plus 1. 49 is the same thing as 50 minus 1. So 50 minus 1 squared is 50 squared, that's easy, minus 2 times 50, that's easy, plus 1, so 2401. Now you have to reduce that modulo 90. So what is 2401 reduced mod 90? Instead of trying to do it all at once, pull out as many multiples of 90 as are obvious. For example, 90 times 20 is 1800, and I can definitely subtract that from 2401, leaving behind 601. 90 times 6 is 540, so take that away. 601 minus 540 is 61. So there we have it. We have a value less than 90, so we're done. So ultimately, 49 squared is equivalent to 61 modulo 90, and it only took us a minute or two. Now I have to square it again, and then I'd have to square it again. And again. And I keep exploiting tricks like this. So we've got 61. Our next step, we have to square it. 61 squared is 60 plus 1 squared. So what is x plus 1 squared? It's x squared plus 2x plus 1. So 60 squared plus 2 times 60 plus 1. That's 3721. Since I'm taking out 90s, I pretty quickly pull out 3600, 90 times 40. Leaving behind 121, I subtract 90 and I get 31. If I square again, I need to square 31. Well, I'm going to do the same thing, calling it 30 plus 1. 30 squared plus 2 times 30 plus 1, 961. Pull out 900, 61. Okay, so now I can say that 7 to the 22nd by the successive squaring algorithm is 61 times 61 times 49, according to the digits of this expansion that were not 0. Now 61 times 61 we already computed is equivalent to 31, so 31 times 49. Okay, x plus 1 times y minus 1 expands like this. So 31 is 30 plus 1, 49 is 50 minus 1, so 30 times 50 plus 50 minus 30 plus 1. Not so bad. We compute that to be 1519. Take away 900 to get 619. And then I just have to take away, let's see, 540 and be at 79. So if we can execute the successive squaring algorithm, including doing multiplication, addition, and subtraction of reasonably sized integers by hand, we can take care of a lot of problems. But there is more that can go wrong. So in the example from a few slides ago, we were given that the base, 704,867, is prime. That meant computing phi of 704,867 did not take work. It's just p minus 1. But you might not always know that the base is prime. So for example, if I wanted to compute 154,867 inverse modulo this enormous thing, we'd have to use the Euclidean algorithm to verify that two numbers are relatively prime. I don't know that that base is prime. For all I know, it's not relatively prime to that other number. Okay, the Euclidean algorithm is pretty fast, so let's suppose we've done that. Now I need to use the successive squaring algorithm to compute 154,867 to this power. Okay, if I can run the successive squaring algorithm quickly, that's not a big deal, right? But what we need to do is figure out what the Euler-Toshin function evaluates to on the base. So what we have to do is find a prime factorization for that number. Now Wolfram Alpha, which I recommended earlier, can do this quite easily. You simply just ask, what are the factors of this number? And it will tell you. But as the numbers get larger and larger, prime factorization gets slower and slower. In fact, both factoring and the successive squaring algorithm get slower and slower as the number gets bigger. However, factorization gets more slow, so it gets much, much slower than the successive squaring algorithm gets. In fact, at a certain point, for numbers sufficiently large, successive squaring can still happen practically instantly on a modern computer. But factoring numbers of that size would take quite literally thousands of years of computational time. So the difference between fast multiplication and slow factoring is a big deal, the basis of modern cryptography, in fact. Multiplying numbers together, or exponentiating via the successive squaring algorithm, is reasonably fast. It does slow down as the numbers get bigger, but it slows down a little bit. Factoring is a very slow algorithm. Factoring a large number, as the number gets bigger and bigger, the factoring algorithm takes way more time. So for sufficiently large numbers, factoring a certain number so that you could compute the Euler-Toshin function is just unreasonably slow. It would take too long. The issue is not that it's impossible. The issue is that it would take literally thousands or millions or billions of years to complete, even on the fastest modern computer.